Hey class, and welcome back to the third installment of Chapter 9, where we're going to be talking about rotational dynamics some more, but now we're going to introduce kind of the last few things that we've learned in terms of work, energy, and momentum in the last couple chapters, but now apply those also to rotational motion. All right, so we're going to talk about rotational work, rotational kinetic energy, and what we call angular momentum in this last section. So as you recall, work equals force times distance, right? And so I had written up here before, I actually just erased it, all of these different equations, but, we had work equals force multiplied by the parallel distance, right? And we had kinetic energy is equal to 1/2 mass times linear velocity squared, and we had linear momentum equals mass times linear velocity. And now we're going to go ahead and fill in each of these equations as they apply to rotational motion, and you'll be able to see the similarities. In fact, I bet you could just guess. What do you think work is? Well, what's the rotational, this is for rotation, what's the rotational analog of force? Torque. What's the rotational analog of linear displacement? Angular displacement, theta. Work is torque times theta. Kinetic energy from rotation, again, I showed you this already, but the 1/2 is still just 1/2. Mass is rotational inertia, and then instead of linear velocity, we have angular velocity, omega. And then for momentum, angular momentum is L, and instead of mass, we have moment of inertia, and instead of linear velocity, we have angular velocity. So that's what we're going to be tackling in today's video and looking at some of the applications. Just to prove it to you, make you convinced, right? Work equals force times displacement, and the displacement for something moving in rotational motion, right? The arc length is just the radius times the angular displacement theta. And we know that torque is just force times the perpendicular distance, which for, again, something going through circular motion, the perpendicular distance to the tangent is just the radius. And so we can see that work is equal to the amount of torque applied multiplied by the angular displacement through which that torque is applied. Again, so like here, if this girl pushing on the merry-go-round pushes for a quarter turn, theta would just be pi over 2 radians. So again, the work for rotation is torque times theta, and the SI units will come out to be equal to joules once again. All right, so again, that weird thing with radians, it changes the direction from rotational or the tangential direction to the radial direction, really, right? And so that's how you're able to change newtons times meters of torque into the Newton meters that turn into joules. So for kinetic energy, just to kind of prove to you what I just put on the board behind me, right? We know kinetic energy is 1/2 mass times velocity squared. If this velocity is the tangential velocity of something moving in circular motion, then we know that V equals omega times R. Substituting that into the equation, we see that kinetic energy is just 1/2 mr squared omega squared. And if you have a bunch of points adding up to make a rigid body, then you can sum up this equation for all of those individual points, 1/2 mr squared omega squared for all of those added together. And so if they're all part of the same rigid body, their angular velocity, no matter where they're at, close to the center or further out, their omega is the same. So you can pull that out because you know that's the same for all of them. And you're just left with the sum of the mr squareds, which is by definition the moment of inertia. So we can find that the kinetic energy of rotation is 1/2 I multiplied by omega squared. So once again, as long as we're using radians, again, because physics is rad, then you should get units of joules for kinetic energy. So I want to do just kind of one shorter example of using kinetic energy, going back to the same yo-yo problem we did earlier today, and then I'll have some more complex examples on foxtail as separate videos. So anyway, here's the same situation where we're just simply holding the string of a yo-yo, and the yo-yo is being released to fall, and it has a mass m, a radius r, and we're going to model it as a solid disk that unwraps or rolls down without slipping. Now, instead of telling me anything about the acceleration, what I want you to do is try to use energy to tell me what the velocity of the center of mass, so how fast will the overall yo-yo be moving down after it's dropped some arbitrary height we're just going to call h. Okay, so now notice I specify the velocity of the center of mass. The reason that I'm doing that is because since the yo-yo is rotating as it falls, different points on the outer edge of the yo-yo are all moving at different linear speeds downward. Because like the part that's rotating up while falling, in theory, could have a momentary linear velocity of 0, whereas the point on the far outside that's rotating down while falling would be moving much faster than even the center because it's rotating down and falling down at the same time. So I want the kind of average velocity of the whole thing, or the velocity of just the center of mass. Pause the video and try using the same conservation of energy technique that we've been doing all through earlier chapters and apply it to this situation. Ready, go. So hopefully you paused it and tried it out. I'm going to now walk you through. We have our picture. We've identified an initial point when it starts with a speed 0 and a final point when it's now fallen through a height h and is moving with some velocity of a center of mass v and with an angular velocity of omega because it's rotating. So we want to use our conservation of energy equation that tells us initial energy plus any work done by outside forces, non-conservative forces more specifically, equals the final energy. And now, since there's no work done by outside forces, all we have is conservation of energy. What form of energy do we have at the beginning? Well, it's stationary, so there's no translational kinetic and there's no rotational kinetic. It's just gravitational potential energy. And final, we have both rotational kinetic energy, 1/2 I omega squared, and translational kinetic energy of 1/2 mv squared. Now again, I notice I specify the velocity of the center of mass there. Okay, so we want to solve for this velocity. We're told that, things like m and h are easy to measure. We know what g is, but we don't know I or omega. Bummer. So we got to do some substituting in. So we know, since it's unwinding without slipping, as I mentioned, that the velocity of the center of mass is just equal to omega times r, or omega equals v over r. And we know, since we're dealing with a solid disk or solid cylinder, once again, we can say I is 1/2 mr squared. So I'm going to pop both of those into my equation here. So I have I as 1/2 mr squared and omega as v over r. All right. So now if you go ahead and solve this, what you can observe, let's see, first of all the m's can cancel, because since there's an m in all three terms. Here I'm going to have r squared on bottom and r squared on top, so the r's will cancel. And so this should reduce to just gh equals 1/2 v squared plus 1/2 times 1/2, so 1/4 v squared. All right, notice, I think this is a typo, this capital V should be lowercase, but it's the same v. So now I have gh equals 1/2 plus 1/4 v squared. 1/2 plus 1/4 is just 3/4. So solving for v, it's just the square root of 4/3 gh. Now what would it be if I just dropped it straight down? If there's no rotation, think back to how we've solved those, it should be the square root of 2gh. So instead of being 2gh, which would be 6/3 gh, we're at 4/3 gh instead. So it's a lesser downward velocity because some of its energy is going into rotation that has caused it to slow down. So boom, that's box worthy. All right, cool. So we've covered work, we've covered kinetic energy. Now we're on to angular momentum. So angular momentum, as we already mentioned, is defined using the letter L, and it's quantified as being equal to the moment of inertia multiplied by the angular velocity, once again, provided that we're dealing with units of radians per second. So our overall SI units for angular momentum aren't real pretty. It's kilograms times meters squared per second is the SI units. There's no fun name that's reduced down to, although it'd be cool if we called them like Gus's in honor of my dog or something, but it's kilograms times meters squared per second. So just like with linear momentum, we also have the principle or the idea of conservation of angular momentum. So if you have an isolated system, like our ice skater here, if you have an isolated system which now means it's free of any net external torques acting on it. Isolated. Yeah, my wife got the joke about the ice. So good. Yeah. If only that wasn't the fourth time y'all have probably heard that joke. But anyway, so if it's free of any net external torques, so there's nothing outside affecting it, only torques within the system between objects that are part of the same system, then the net angular momentum will remain zero. So a cool application of this is the idea of a figure skater. If you've ever watched somebody figure skating, they hold their arms out, right? Get themselves rotating, and then they pull their arms and maybe a leg, their limbs inward towards their center. As they're doing that, they're reducing how much mass is spread outward. So as they're pulling their mass inward, they're decreasing their moment of inertia. And since angular momentum is conserved, then they still have the same angular momentum, and as a result, their rotational velocity must increase. Okay, so that's why they start spinning faster and faster. Stay tuned for some kind of demonstration videos I may make in the next week of this idea, because it's super cool to see visually. Ha! My wife wants to know if we're going ice skating. Maybe we will, but I was thinking of the spinny chair. So one neat application of this is something known as precession also. I don't know if you've ever noticed, but if you watch like a spinning top, as it rotates very fast about its central axis, but it also has this like slower sort of wobble, this wider rotation that it also undergoes, and that's precession. That's because gravity is pulling on it and constantly changing the direction of the angular momentum, which is kind of a cool idea. So not only do tops wobble as a result of precession, but the Earth is actually doing the same thing, right? We're like a top spinning in space, right? Once every 24 hours, we spin around our axis. So our axis is actually changing where it's pointing in space. And while right now it's pointing towards the star Polaris, approximately, which we refer to as the North Star, if you wait for, solid 15,000 years or so, our axis is gradually changing and will be eventually pointing towards the star Vega. And so, in fact, this also means that over that time, because the axis tilt is responsible for our seasons, the way that the seasons line up with our calendar will actually change. So gradually, summer will move from starting in late June to moving into starting in July and August and so on, until eventually our seasons will be entirely flipped, just in terms of how they line up with the calendar, which is sort of weird to think about. So here's an example I want us to do, okay, or I want you guys to do, thinking about conservation of angular momentum. So here's none other than Sir Albert Einstein himself. He's standing on a rotating table that we're going to assume is frictionless, so he's in an isolated system. He's going to hold two 5-kilogram dumbbells out, one in each arm, and he's going to get himself rotating. Since it's Einstein, he's going to get himself starting with a rotational velocity of pi radians per second, or 3.14 radians per second. And so let's assume for his body, just his body, you're going to have to add in those dumbbells, but for his body, the moment of inertia when his arms are out is about 3 kilograms times meters squared, and when his arms are in, it's about 2.2 kilograms times meters squared. All right, let's assume that the dumbbells, when he's holding them out, are each about a meter away from his central axis, and then when his arms are in, it's only about 20 centimeters away from his central axis. Okay? With that in mind, I want you to tell me, how fast will he be spinning after he brings his arms in? Ready, go. So hopefully you solved this one. And again, you're following the same basic ideas that we dealt with when we did conservation of momentum the first time back in chapter 7. So we have a situation where Einstein's in an isolated system, therefore the angular momentum before and after this transition should be constant. We know angular momentum, since there's only one object, just Einstein here, it's just going to be equal to I times omega before equals I times omega afterwards. We know the initial omega is the pi radians per second. The final omega is what we're trying to find. So the question is, what are the two I values? Some of you might want to just pop in 3 and then 2.2 and go to town, but that's not accurate because that's just his body. The total I of the system is the I of his body with his arms out plus the I of each of the two dumbbells. And final is the same idea. Again, it's the moment of inertia of his body with his arms in, plus the I, the moment of inertia for each of the two dumbbells when in that position. So you take the moment of inertia of the body plus two dumbbells that are 5 kilograms each at 1 meter away squared, because it's mr squared, right? And we find that the moment of inertia with his arms out adds up to 13 kilograms times meter squared, and with his arms in, it comes out to be 2.6 kilograms times meter squared. And so if we go ahead to solve for our final omega, what we find is that our final omega is 13 kilograms times meter squared times pi radians per second divided by 2.6 kilograms times meter squared, and you get 15.7 radians per second, which I believe looks like it should be right about 5 pi radians per second squared. So by pulling his arms in just 80 centimeters each, he increased his angular velocity by 5 times. He started spinning 5 times as fast. Boy howdy. Box-worthy answer right there. All right, so that just about wraps things up, and there's more kind of complex examples of all of these ideas because there's really a lot here in this chapter 9 that you can find on Foxtail. But the last kind of cool application I just want to talk about is riding a bicycle. I'm guessing just about all of you have probably ridden a bike at some point in time. One fascinating thing, have you ever noticed, right, to stay balanced when you're riding straight down the road, you always have to stay very vertical. Your center of mass, center of gravity needs to be over your very small base of support, which is where your tire's on the ground. If it's not, if you lean too much one way or the other, you'll start to fall. But if you go around a turn, you have to lean, otherwise you will fall over. Why is that, do you think? Why do you lean while turning, and why don't you fall over while turning when you do lean? It's kind of interesting to think about, right? Well, let's look at it in terms of thinking about torque, all right? So first question to ask yourself is, when you're going around a turn, so here's a bike rider you see in this picture. Let's imagine he's going to be taking a left turn. So what force supplies the needed centripetal force to make the turn? Well, there's only really one option, right? That's the force of friction acting on the ground, pushing inward towards the center of his circular motion as he goes around a curve. So if this is your rider here, and if he tries to make the turn perfectly straight up, this friction force is at a lever arm distance here away from his center of mass, which would be a point around which he might rotate. And so there's a torque that's going to make him want to tip over generated by that friction force. So that friction force pointing inward at a distance r1 away is going to cause him to experience an angular acceleration in the clockwise direction to tip over. In order to prevent yourself from tipping over, you must need some secondary torque to counteract that. And the only other force acting on you that can generate that torque is your support force, the normal force from the road pushing up. But if you don't lean, the lever arm distance for that second force is 0, and so your restoring torque, that second torque from the normal force, is also 0. So your net torque is just the friction force times r1. You experience an angular acceleration and you fall over. Many of us, first time we ever learned to ride a bicycle, that happens. We try to take a turn, we try to keep real straight up and down because that's what we learned works on bicycles, and we start to fall over. Hopefully you kick your leg out and don't completely crash, but maybe you did and you're stronger for it now, right? So instead, when you go around a turn, you're going to lean, something like this, right? I love watching speed skating in the Olympics, right? Especially the new short track stuff, because you see how these guys lean going around a turn, right? Because you need to have a balanced torque. There's a torque generated by the force inward that provides your centripetal force to make the turn, and as you lean, you create a distance away from your center of mass for that support force, for the normal force that generates a restoring torque. And so if you do it right, if you lean the right amount, these two forces will generate two torques that are exactly equal and opposite to one another so that you can remain in equilibrium while going around the turn. And this is actually a fun fact. One time I was riding my bike to grad school, I still remember this quite clearly. I went to grad school in Colorado. I was riding my bike, went around a turn, and I was doing this in the wintertime. I rode the bike kind of year round, or at least tried to, and I hit a patch of ice. Guess what happened? I was leaning, I was doing my physics just right. I was like, all of a sudden, the force that generated my centripetal force, that inward pointing friction force, as soon as I hit the ice, boom, that was gone. So what we call the tipping torque was gone. But I still had the torque generated by my normal force because of my lean. And so guess what happened? I experienced an angular acceleration, and this time counterclockwise, and the bike fell over. Somehow, though, I managed to stay on my feet. I straddled my bike and slid across the ice as my bike fell to the ground. I felt cool and was kind of pumped about it, but I think people just thought I was weird when I celebrated after falling over. But anyway, so that's a fun example of torque and some of its applications. Just wanted to share that with you guys. But this wraps up chapter 9, and again, wraps up our application of everything we've learned all semester long as we apply it to rotational motion. Pretty cool, right? So yeah, that wraps up this section, and tune in next time for some discussion of fluids.